Welcome to EPA's monthly webinar series for small drinking water systems. Today's topic is disinfection residuals. So we have a webinar phone number there if you need webinar support during our webinar. Also, if you want to ask a question for any of the speakers, and we'll answer the questions after both speakers are done. If you have a question, please put it in the question, which is a dialog box up in the in one of the boxes up to the upper right, I believe, of your screen. Type in the question. Also, if you've missed our poll for how many people are in your room, and you have more than one person in the room, so only the people that have more than one person in the room. If you could put how many people are in your room in the question box and just send it to us, that helps us document how many people are attending the webinar and how valuable it is. And speaking of which, if you have a story about how the webinar series has been useful to you, your utility, or your agency, please send us a little note in the questions box and we'll record it. That again helps us justify this webinar series. I should note that a certificate of continuing education contact hour is offered during this webinar. The requirements are that you must be registered for the webinar or in a room with somebody who is registered. You must attend for all 60 minutes. If you are in a room with others, the people not logged in must be provided by the person who is, and you can send the names to that email address. Also, if you did not request the credit at registration, again, send your request to that email and we can take care of it. The certificates of completion cannot be provided for viewing the webinar recording, which will be put on EPA's YouTube site. So with that, we'll go to our first speaker. Our first speaker is Matthew Alexander. Matthew is an engineer with EPA's Office of Groundwater Drinking Water in Cincinnati, Ohio. As a member of the agency's area-wide optimization program, he supports various optimization approaches and provides technical assistance related to distribution system water quality, with particular emphasis on maintaining disinfection, residual, and storage tank operation. Matthew has a BS in civil engineering and an MS in environmental engineering, both from the University of Cincinnati. Matthew is a registered professional engineer in the state of Ohio. And with that, I will pass it off to Matt, and he will give our first presentation.
All right, well, thank you, Tom. So today in my presentation, I'm going to be talking about how to develop a monitoring plan, a disinfection residual monitoring plan that's representative of an entire distribution system. I'm also going to talk about how to collect samples that accurately characterize water quality, and also discuss some common interferences and limitations with some of the chlorine residual field methods that are commonly used. So why is it important to develop a disinfectant residual monitoring plan? Chlorine residual data is really the only way to assess whether or not a disinfection barrier is in place, so collecting a reliable, accurate data is very important. So today I'm going to discuss some of the steps that can be taken to collect reliable chlorine residual data in your distribution system. So here are some of the learning objectives for my portion of the presentation. So after participating in this presentation, participants should be able to develop a monitoring plan that is representative of their entire distribution system. They should also be able to collect samples using a consistent, technically sound approach that ensures that water from the distribution system is being accurately characterized, and also understand interferences and limitations of some commonly used chlorine residual field methods. And here's just a basic outline of a few things I'm going to discuss. First, I'm going to briefly provide some background information about the program that I'm involved in at the EPA. So hopefully that will help provide some context for some of the other topics I'm going to cover. Then I'm going to discuss why monitoring location selection is important, and then share a sample collection procedure that we've developed. And then finally, I'm going to discuss some of the limitations and interferences with some of the field methods. So at the US EPA, I work in the Office of Groundwater and Drinking Water, and I support the area-wide optimization program. AWOP encourages drinking water quality beyond compliance levels to increase public health protection. And our program relies heavily on system performance data. And we help build operator capability and encourage operational changes before design changes are made. And we really, like I said, we rely a lot on data as far as data quality or data integrity because the data, the performance data that's collected is assessed relative to optimization goals that we've developed, which are often more stringent than the regulations. So with that being said, the information provided in this presentation is in the context of optimization, which often exceeds regulatory requirements. So our program originated back in 1989, and initially we focused on microbial optimization at surface water treatment plants. And since then, our program's expanded into several other areas, including optimization of disinfection byproducts, distribution system optimization, optimization of membrane filtration, and we're starting to get into harmful algal bloom optimization as well. And today, probably about half the country participates in our program as far as states, so about 25 states and 5 EPA regions have some level of involvement with the AWOP program. So now I'm going to switch gears a little and start discussing monitoring location selection. So sample locations should be geographically distributed throughout the system and be representative of a range of water age. So as you can see in the map on the right of your screen, this is just an example of a disinfection residual monitoring plan that a water system we worked with developed. And as you can see, a lot of locations are spatially distributed. They're not only in locations of the system near the treatment plant, which is in the bottom right where some of the green dots are, but it's also in some of the more remote areas of the system as well. The revised total call form rule specifies the number of samples that a system should monitor per month based on the population they serve. However, it leaves the number of monitoring locations to the state or water system's discretion. So less samples at more locations is preferred, opposed to more frequent samples at fewer locations. And in our program, we really encourage systems to conduct additional investigative sampling in addition to the compliance sampling that they conduct to really try to target areas of poor water quality in the system, and we call this investigative sampling. And just based on our experience with working with various water systems, we've observed that systems often select monitoring locations that are often, based more on convenience. So they're often located at, restaurants or businesses that are typically located along main roads, which often have main large transmission lines that run along the roads, and they don't really target more remote areas of the system. So that's something we really try to encourage, is to try to get just a variety of sample locations. And also, once a monitoring plan is developed, sample locations may need to be added or removed over time because systems change. Water quality changes, system hydraulics can change. So we recommend that once you have a monitoring plan developed, you go back and reevaluate it on a periodic basis. So these are some suggested monitoring locations that we think systems should consider. We strongly encourage systems to monitor at their treatment plant effluent, as well as any other metered connections they might have. And these are important because they help establish a water quality baseline to have an understanding of what the water quality is entering the system. We also think it's a good practice to monitor chlorine when systems collect their disinfection byproduct samples. And this is in particularly valuable with total trihalomethanes because over time, a system can start to establish a correlation between chlorine residual and THM levels in their system, and that can be a valuable process control tool for distribution system operators. Also, storage facility design and operation can result in water quality degradation. So we suggest that samples are collected at or in the proximity of storage facilities. And particularly when storage tanks or facilities are draining, that's a good time to sample, especially at the end of their drain cycle, because if the tank is poorly mixed, it's likely that some of the poorest water could be coming out at the end of that drain cycle. And also, if available, online chlorine analyzers can also provide valuable data at storage facilities if the water system has the resources to install those. If a system has booster chlorination facilities, we strongly encourage that samples are collected both upstream and downstream of those. And that just allows the system to understand what levels of chlorine they have entering and leaving the booster facility. And also, if a system has a variety of pipe material, we strongly suggest that they select sample locations that characterize all different types of pipe material throughout their system. In particular, unlined cast iron or cement line pipe at times are known to cause water quality issues, so it's also important to evaluate those. And as I mentioned earlier, it's important to target areas of the system where the poorest water quality is anticipated. You know, in areas where there might be vacated customers or dead ends, if there's, you know, larger diameter lines than what the system suspects they need in certain areas of the system where you would have high water age, those are great places to look. So next I'm going to discuss our calculated flush time approach, or how to collect a representative sample. What we've learned just by working with various water systems is that flushing practices really vary significantly throughout the industry. And we've seen a lot of different things. I'm just going to talk about a few here. One approach that we've seen operators use is flushing based off of temperature changes. And also, there is some technical basis for this, but this can be a challenging approach to use certain times of year where water temperatures are similar to ambient air temperatures. So they might not be able to determine when they flush an adequate amount where they're pulling water from the main. So we try to discourage this approach if possible. We've also seen systems just use a standard or a constant flush time at all locations. Also, I mean, this one-size-fits-all approach might work, but in some cases they might not flush a sufficient amount at certain flushing locations. So we try to discourage that as well. And probably the worst case that we've seen, which we have seen this a few times, it's where systems will flush until they get a good compliant sample. When I say good, I'm doing the quote thing. This isn't a good approach for various reasons. You want to be able to flush where you're characterizing water quality that's immediately in the main, and you know, to get a sample that's representative of what you're actually flushing at the time. So oftentimes, like I said, flushing approaches don't have a strong technical basis, and as a result, we have developed this calculated flush time approach for operators to use, which is pretty straightforward. And basically, it consists of estimating the volume of water that needs to be flushed. So you'd estimate the length of line as well as the diameter of the service line leading up to the location where you're collecting the sample, between that location and the water main. And then next, you would measure the flow rate. If possible, you would do that with a measuring cup or a graduated cylinder, or we have developed a sampling device, which I'll talk about here in a second, that has a flow regulator, so you're going to be flushing at a constant flow rate. And once you know the volume you need to flush and the flow rate, it's easy to calculate the time needed to flush just to exchange the volume of water in the service line between the sample location and the distribution main. So we like to include a factor of safety when doing this as well, just to ensure that you're actually getting water from the main. This approach is pretty universal. It applies to both sample taps in buildings as well as hydrants. When you use this approach in buildings, it can become a little complicated because at times the configuration of the premise plumbing is unknown, so you have to do some estimation. Sampling from hydrants for chlorine residual is a preferred approach because it's much more straightforward and it's much easier to calculate the flush time at those locations. We like to use the hydrant sampler, which is a device that we developed in our program to collect samples from hydrants in the distribution system. And hydrants are preferred as well because you can collect samples without disturbing their residence or business, so you can quickly go in and collect your sample and leave. So for more information about the hydrant sampler, I've included the link here in the slide, so feel free to visit that. We've got instructions on how to build one and also some videos demonstrating how they can be used. And I'll show a photo of the hydrant sampler here in the next slide. So this is one of our earlier versions of the hydrant sampler. Since then, we've got a more compact version, but this just gives you kind of an idea of what that might look like. So next I'm going to talk about some of the commonly used chlorine residual field methods. The colorimetric methods are the most commonly used in the field. They're relatively quick and easy to conduct, and they also provide relatively accurate results if they're conducted correctly and the operator is aware of interferences and potential limitations associated with the method. So I'm going to talk about the various issues with the different methods here in a moment. In our optimization program, we really discourage the use of the color wheel. I know in some of the small rural systems across the country they still use those, but we really try to discourage that because they have poor sensitivity at low concentrations, and you'll also get variability between operators. So what one operator might read, the other operator might interpret a different value. So we really prefer using colorimeters. They give you an actual number that you can record, and oftentimes they're more accurate and precise, especially if they're properly maintained and adequately functioning. So there's different models and manufacturers out in the market. We strongly suggest that you consider both the cost of the instrument as well as the cost of reagent when selecting an instrument, and also consider the functionality of the instrument. Some instruments just measure a single parameter, and there's other ones out there that measure various parameters. So depending on your budget and your needs, those are some things to consider. There are colorimetric methods for free chlorine, total chlorine, as well as monochloramine. So in the next few slides, I'm going to talk a little bit about each of those different parameters. But first, I'm going to talk about some general best practices. First of all, it's strongly recommended that the performance of your colorimeter is validated with secondary standards prior to use. It's a best practice to verify performance and document the results, and also confirm that the secondary standards aren't expired. We have seen systems use these, although they're expired. So, although it's a good approach, you want to make sure that they're still valid. If your instrument doesn't pass the verification, don't use it. Contact the manufacturer, and they can help you troubleshoot and possibly repair the instrument. Depending on the particular instrument you're using and the manufacturer, some of the newer technologies might require periodic firmware or software updates. These updates might be needed to make corrections to certain programs or to improve performance of the instrument. So it's a good practice to periodically check if new updates are available. It's not always easy to know when the new updates are out there, so we recommend checking the manufacturer's website. And another note, just depending on the instrument, there might be multiple programs available for the same parameter, so confirm you're using the correct program for the desired range of parameter you want to use. So for example, one of the more popular instruments out there, they have a low range, a mid range, and a high range total chlorine and free chlorine method. So depending on the anticipated chlorine residual that you're expecting to measure, you want to select the appropriate method that's going to give you the most precise results. So the high range method, it reports chlorine residual out to 1/10 of a milligram per liter, and the lower range reports it out to 1/100th. So if you're in the lower range, you obviously want to use the lower range method if you can. And also, depending on the parameter and the detection range of the method, you might have to use a specific type of sample cell. Some of the popular manufacturers, they have glass sample cells and plastic sample cells. The glass sample cells are commonly used for the lower range method or the mid-range method, although the high range method uses a plastic sample cell. So make sure you're using the right cell. Some of these things we take for granted, but we have seen operators make some of these mistakes. It's also a good practice to check the condition of your sample cells as well. They should be clean, free of scratches, and not discolored. If they look defective, replace them. Oftentimes we've seen operators just leave these cells laying in their truck and they'll get scratched up, and that can compromise, I guess, the integrity of the data or the results you're getting. So keep that in mind. We also recommend using separate dedicated sample cells for each parameter. Trace levels of reagent for one method can interfere with others, so it's a good practice to label the sample cells and the sample cell caps. And also, depending on the method and instrument being used, the sample cells might need to be orientated in the instrument a certain way. So I know for the monochloramine method, they suggest, or they tell you to put the cell in at the 2 o'clock position on the clock, versus some of the other methods it doesn't really matter. So just make sure you're putting the cell in the instrument the correct way. And also, depending on the method you're using, a specific type of reagent will be needed. There's separate reagents for each parameter, and there's also different reagents depending on the detection range. So, for example, reagent for a 25 milliliter sample volume is used for the mid-range method, but a 10 milliliter sample volume is used for the low-range method on the DPD chlorine methods. So And last but not least, it's also a good practice to check the expiration date of your reagents and don't store them in extreme temperatures. Once again, some of these things seem very obvious, but these are pretty common issues that we've seen working with various water systems. And just a few more general best practices before I get into some of the specifics with each method. Even in the absence of chlorine or other interfering compounds, a small amount of color formation can still occur when reagents added to water. This positive interference can result in an artificially high result. So this is in particularly important in states where a minimum residual requirement is just trace. This difference can make you think in your compliance, but you may not be. So this is something to definitely pay close attention to in those states where they just require a trace. You can't account for this though. You can do what's called a reagent blank. And this is basically where you take deionized water and then you add the reagent to it, and then you'll just record the value. So whatever value you determine, you would subtract that from your other measurements to compensate for this adjustment. So in some of the newer instruments out there, some of the newer models, they have functionality built in where it will automatically compensate for this reagent blank, and those are really convenient. So if your instrument has that option, be sure to utilize that. And also, if the water sample is not collected directly in the sample cells, we recommend collecting samples in a clean glass container. Plastic containers can exert some chlorine demand, and also dirty glass containers also obviously can exert some chlorine demand, so make sure you're collecting samples in clean containers. And we also recommend analyzing the samples as soon as possible, or as soon as reasonably possible. Chlorine can decay or does decay over time, so the sooner you can analyze the sample, the more accurate results you're going to get. And also try to avoid leaving the sample cells in the sun because chlorine will degrade from UV degradation. And just a few other things. It's also recommended to wipe sample cells with a cloth, a lint-free cloth, prior to analysis. Oftentimes we'll see condensation form in the cells, but you can also get grease and fingerprints, and that may interfere with the results. And as I mentioned with condensation, this is something we see quite a bit, especially in the summer. When it's a warm, humid day and you're collecting a cool sample, you will quickly get condensation on the outside of the sample cell, and we have seen that cause erratic results at times. So we recommend wiping off your sample cells. And also, before zeroing or reading the sample, confirm that the instrument cap is placed securely over the instrument. If the cap's not securely on, ambient light could interfere and cause inaccurate readings. So next I'm going to get into some details about some of the specific methods. First I'm going to talk about free and total chlorine DPD methods. There are a variety of chemicals that are commonly found in finished drinking water that can interfere with both free and total DPD reagent. In particular, high acidity and alkalinity can result in a negative interference. Also, extreme sample pH can exceed the buffering capacity of the reagent, which can also result in a negative interference. And there's also various oxidizers, including bromine, chlorine dioxide, permanganate, organic chloramines, and ozone, that will result in a positive interference. And also oxidized iron and manganese can result in a positive interference. So there's a few things you can do with some of these interfering compounds. If the acidity or alkalinity is excessive or the pH of the sample is extreme, you can adjust the pH of the sample to a pH between 6 to 7 to minimize this interference. And also, if permanganate is present in the water, you can also pre-treat the sample with potassium iodide and sodium arsenite to correct for this interference. However, unfortunately, there's not really a great remedy to avoid some of the other interfering compounds that I discussed. So although you can't do anything to compensate for those, just building awareness and knowing that if these compounds are present, they can result in interference, can be valuable for operators to know. So next I'm going to talk about the free chlorine endophenol method. This is a relatively newer EPA approved method. It was just approved last year for compliance. This method is in particular valuable in situations where you have interfering compounds that might interfere with the DPD reagent. You can use the endophenol method because it's not prone to as many interferences. However, this method is prone to interferences with ozone and sulfide, but typically you don't see those compounds in finished drinking water. This method's a little different. It uses plastic sample cells, and like I mentioned earlier, those are prone to having some issues. In particular, you can get these fine air bubbles that will form on the inside of the sample cell. And that's pretty common with this method. So what you can do to compensate for that is just slowly invert the sample cell or shake it prior to analyzing the sample. And with the endophenol reagent, it's very temperature dependent, so we recommend checking the manufacturer's standard operating procedure to determine the appropriate reaction time depending on the temperature of your sample. So next is the monochloramine endophenol method. This method is kind of similar to the free chlorine endophenol method, or it uses some of the same chemistry. So it's also prone to some of the same interferences as that. However, this method specifically measures monochloramine residual opposed to total chlorine, which some systems use that chloraminate. So we like this method because it quantifies the active disinfectant in a chloraminated system, and this can be a valuable method for process control. This method, however, it's not an approved EPA method for compliance monitoring. And like I just previously mentioned, this is prone to some of the same issues or limitations as the free chlorine endophenol method. So here's just a table just to summarize some of the advantages and disadvantages of each of the methods. Free and total chlorine DPD method is probably the most commonly used methods. They're both EPA approved. However, they are subject to several interferences with various compounds. The free chlorine endophenol method is less susceptible to interferences. It's also EPA approved, but it still has some issues, and it hasn't been as widely used at this point as the DBD reagent. The monochloramine endophenol method, the good thing about it is it specifically measures monochloramine residual. However, it's not an EPA approved method, and it's prone to some issues with temperature and also air bubbles that form in the cells. So this kind of wraps up my presentation, but I just want to hit on some of the key things that we discussed throughout this. So when assessing the disinfection barrier in the distribution system, monitoring location is crucial. It's important to sample in critical areas of the system that may not be captured in some of the routine compliance monitoring plans. And through our optimization program, we really emphasize that operators have the mentality of going out in their distribution system and finding areas of low chlorine residual, because we feel like you have to go out and find areas of poor water quality before you can make operational changes to improve water quality. And also, adopting a technically sound sampling approach is an important aspect of collecting reliable chlorine residual data. If the sample site is not flushed in an appropriate amount of time, chlorine residual cannot be accurately characterized. And also, field methods aren't perfect. Like any methods, they're prone to certain interferences or limitations. However, you can still obtain accurate, reliable results if you're familiar with the nuances of the method. Just because a colorimeter gives you a number doesn't necessarily mean it's an accurate number. And also, just most of the information that I've discussed in this presentation, in particularly related to the methods, a lot of that I've just got from the manufacturer's website and through some of their operating procedures. So I strongly encourage you to reach out to manufacturers if you have particular questions about some of the methods or some of the instruments that you're using. They can really be a great resource. So this concludes my portion of the webinar.
Okay, thank you very much, Matt. And we will now go to our second speaker. A few things that we need to do for housekeeping. Again, if you missed the poll in the beginning and you have more than one person in your room, please put that number of people in the question box. It's a dialog box on your screen. Put how many people are in your room in that box if you have more than one. Also, I failed to mention in the beginning that if you want to look at the slides themselves, they can be found in the handout section of the dialog box. So if you want to pull them up, you can pull them up there. Also, in addition to putting in the number of people, if you have a story or a note of how the webinar has been successful for your work, with regard to your work or your utilities or your state's work, please drop us a note. We'd love to hear about that. Okay, our second speaker will be Jonathan Pressman. Jonathan Pressman's a research environmental engineer with the Water Supply Water Resources Division of EPA's Office of Research and Development in Cincinnati, Ohio. His research work includes disinfection byproduct formation in drinking water sources, membrane processes for drinking water treatment and natural organic matter concentration, and disinfection and nitrification in drinking water distribution systems, with emphasis on minimum residuals, molecular genetics, and microbiological engineering. Dr. Pressman has a BS in Civil Engineering from Cornell University and a Master's and PhD from the University of Texas at Austin. He is a registered professional in both Ohio and Texas. So I'll hand the podium to Jonathan Pressman, and we'll answer questions for both speakers at the end. We'll hope to get to a few before the end of the hour, but usually we stay an additional half an hour to answer all the questions. So keep them coming.
Thanks, Tom. While I wait for the slides, let me show my screen. Okay, as we get started here, I want to first acknowledge my co-authors on this work, David Wahman and Matt Alexander, who you just heard from, and David Wahman is here with us in the room to help with any questions. But also equally as importantly are all of these contributors. I don't have time to read every name here, but just to say that this work was done by a whole lot of people, and I certainly need to acknowledge all of the people here. So the objectives of my talk today are to review the history of distribution system chlorine monitoring siting, review state regs and guidance that deal with where to take samples, talk about a case study demonstrating chlorine monitoring locations evaluation, and then I'm going to switch gears a little bit and talk about an evaluation of 6-year review 3, information collection rule, disinfectant versus bacterial data, coliform and E. coli. So the story starts back in 1975, and some of these slides have a lot of words on them because I try and keep regulatory language complete. I'm going to point your attention to various areas, usually with red text and actually my mouse as well. So the story starts back in 1975. It really goes back to 1962 to the Public Service Health Standards of 1962, and it may even go back earlier than that, but that's where I traced it to. As far as EPA, it goes back to 1975 to the National Interim Primary Drinking Water Regulations. And pointing you to the red text here, provided that the supplier of water takes chlorine residual samples at points which are representative of the conditions within the distribution system at the frequency of at least 4 for each substituted microbiological sample. So back in 1975, you could substitute coliform sampling, you could substitute chlorine sampling for coliform samples at the rate of 4 to 1, and you were instructed to take those at places representative of the conditions within the distribution system. So that's sort of the first place that this representative language that we see that. Now we jump ahead to the total coliform rule all the way to 1989. And in the preamble to the TCR rule, I get the language that you see on this page. And I call your attention to the top, where in the preamble to the 1989 TCR rule, EPA notes that in 1987, when they proposed to revise this provision by requiring systems to collect samples from at least 3 times the number of sites every year as the number of monthly samples required. So it was proposed to go collect samples at more sites than samples. And EPA received numerous comments on that issue. Most commenters opposed the proposed requirement. Many commenters claimed that the increase in the number of sampling sites would force systems to use private homes with possible problems of access, or that the requirement would preclude systems from monitoring water quality at specific representative sites over time. So the final rule in 1989, which is what the slide refers to, is the red text at the bottom. Each system must develop and monitor according to a written sample siting plan, which is subject to state review and revision. The state must develop and implement a process which ensures the adequacy of the sample siting plan for each public water system in the state, including periodic review of each system's plan. So the 1989 TCR rule left this up to the states, and the states could determine what was adequate for how many not how many samples, but where to take the samples and how many sites would be required, and that would be in a sample siting plan. And then we jump ahead to the current regulations, which are essentially the same. 141.72b on the top talks about the residual disinfectant and then specifies the 141.74. So we go to 141.74, and that's where it talks about residual disinfectant at the same place. You need to take those at the same time as total coliform samples, and it references the two items below. 141.21 is before the revised total coliform rule. 141.853 is the revised total coliform rule. And so pointing you down just to the red text on the bottom, systems must develop a written sample siting plan that identifies sampling sites and a sample collection schedule that are representative of water throughout the distribution system. So the language is still very similar. So it's really left up to the states. So the next step, we went to the states, and we conducted what I'll call a preliminary web-based search. So we went to state websites to see what information we could find out about what they require about how to determine your sample sites, how many sites, and how to determine those. And we found more or less 3 general categories of states, and this is not an exhaustive search. These are just the things that we could find easily online. If people from various state agencies would like to email me at the end, my email is on the last slide, and want to provide me information about your states, that'd be great. So we found 3 general categories. The first was where a state prescribes the minimum number of sample sites, and here's a handful of states that do that, and I'm going to go through examples of what they prescribe. And then general guidance on what representative means, and so a few states here, New Jersey, Oklahoma, Tennessee, where general guidance on representative we found, and then some states where we found no additional guidance. And that may not mean that the states don't have any, it just means we didn't find it on their website. So going through sort of some of the most interesting ones, the specific sample site number requirements, these are generally based on population and the number of samples required. So I'll start with Texas. In their guidance manual, RG 421, they have a chart with population served, the number of total coliform samples, and the number of routine sample sites required. So you see that for the smaller populations, you have 1 times the number of samples. So that would be an equal number of sites required per sample, or 1 to 1, I guess. And then as the utilities increase in size, it goes down to half the number of sites as samples. New Mexico has a similar table, but they have a multiplier to obtain the number of sites, and as you get up to their larger cities, it's a multiplier of 1.5. Next slide. Okay. South Dakota has a similar table with routine samples per month and number of routine sites. The numbers turn out to be fairly similar to Texas, where for the smaller cities, it's about half the number of sites as number of samples, and as you get up to the largest category, I'm sorry, for the smaller cities, it's about 1 to 1, and as you get to the larger category here, it's about half or so. North Carolina had language that listed at least 2 to 3 times the number of sampling sites as required according to the system's population. Kansas had some instructions to divide the distribution map into a number of zones, the same number of zones as bacteriological samples required. and then select 5 sites within each zone. However, the last step here at the bottom, it says rotate through the sampling sites and collect 1 in each zone. So you have a lot of sites, but the number of samples per month would be equivalent to the number of samples you're required for TCR, so that's 1-to-1. Louisiana is the last example here. They have a pretty new rule in Title 51. Section 903, the coliform routine compliance monitoring, specifies that your points of collection monitoring sites should be 1.5 times the minimum number of samples required. And then they have a specific Section 367, disinfectant residual monitoring and record keeping, that says you should monitor at the coliform sites and additionally add a number of sites equal to 0.25 times the number of total coliform sites. And then the last item, number 3 below, is once a day at the maximum residence time site. So that's a handful of states that have specific requirements. Then we get into a little more general category where general advice is given. So for example, in Oklahoma, they specify to monitor at areas of concern in the distribution system represented to include things like dead ends, low pressure zones, areas with longer retention times, upstream and downstream of storage tanks, areas serving water from different sources. So very much what you heard from Matt a little while ago. Tennessee is similar. I'm going to skip right here to number 3, which is interesting. The goal should be to collect at least 30% of the required samples from residential areas. For the purposes of this plan, residential areas are defined as locations in the distribution systems which are served by the smallest distribution lines. And then they have other guidance such as dead-end lines, low-use areas, areas near storage tanks. So very similar. So as you can see from all of this, the guidance and regulations by various states is pretty diverse on how states treat how many locations and how to locate these locations. What I'm going to move into now is a case study, and this is really what brought this to our attention early last year and helped us become interested in how to cite and where to cite samples. We were asked last January, a year ago, to assess chlorination in the distribution system in Flint, Michigan to ensure the disinfection residual barrier was in place. Flint is a city with about 100,000 population. That puts them in a category to measure about 100 monthly TCR samples, and they had been doing that at 10 locations 3 times a week. This was what I'll call a legacy sampling plan. It had probably been going on for 30 or more years, and you know, I suspect there are many utilities out there that have had plans in place for a really long time, and one person teaches it to the next. And so their plan looked a little bit like this map. These are the 10 locations. The sizes I show, the inches, are the service mains that are most adjacent to those sampling locations. And if you were to put this on a map with the major thoroughfares, these would end up being among the larger pipes and some of the larger business areas of the district. And so when we arrived last January, we really wanted to see what was happening in the neighborhoods where people were consuming the most water. And so we felt that it was justified to do more monitoring in areas embedded with residences, which represent the smaller diameter distribution system network and the more aging water. We had about a week to implement a monitoring plan, so we mapped all the public locations, schools, churches, child cares, the places that are public but embedded in the neighborhoods. And we developed sectors like Matt, I believe, was talking about. And so the map shown here is my handwritten, what I was using in the field. The blue lines are the sectors that we developed. And we went out to investigate areas closest to the primary residential water usage. When we found promising sites, we measured the service lines and the diameter, the length and diameter. We measured the flow rates, and we calculated flush times that would be representative of getting water from the distribution system. So we were able to add 24 monitoring sites that were mostly churches, schools, and child cares, and were mostly embedded in neighborhoods. Combining that with the utilities 10 sites gave 34 chlorine monitoring locations weekly. These concentrations were mapped on EPA's website and updated bi-weekly. You can go to the website shown here and see a GIS mapping of these concentrations for the entire year of 2016. EPA has since discontinued the monitoring of the 24 sites that we were monitoring. We did that at the end of December. And starting in January, the city of Flint has a revised monitoring plan where they are now monitoring more locations. And so the city of Flint has been working very hard to expand their monitoring and measure more representative monitoring locations. So as an example for this case study, we're going to look here for a moment at the week of June 13. Shown on this map are the 10 utility TCR monitoring locations. We worked all year with the utility, and they worked really hard to implement best practices. These included maintaining minimum chlorine residuals that were greater than detectable, and to implement a flushing program for areas that had basically localized low flow. And so one of the best practices that we worked hard to incorporate into Flint was to maintain chlorine residuals greater than 0.2 milligrams per liter throughout the water distribution system. This is a pretty well documented best practice. It's in the AWWA Partnership for Safe Water. It's in the 10 state standards and elsewhere. And so when we mapped our locations weekly, we used a coloring scheme. This wasn't a regulatory coloring scheme. This was an operational coloring scheme. So we used the classic green, yellow, and red so we could quickly see areas of concern. And so green means the chlorine concentration was greater than 0.5 milligram per liter. And really was probably pretty healthy. Yellow means that it was between 0.2 and 0.5, and that essentially meant operationally that operators should keep, and EPA and Flint and everyone should keep an eye on that area. Some future intervention may be necessary. And then red locations mean that the concentration was less than 0.2, and some intervention was probably necessary. And so looking here at the 10 sites, now look at the map, and we go to the next slide, and you see that when we incorporate the additional 24 sites, there's about 10 more yellow spots and one red. And so you get a slightly different picture of what's happening when you get into the neighborhoods. And so I write here enough sites as somewhat of a rhetorical question. I'm not going to answer that question today because I don't think there's a single easy answer, and that's certainly up to states to decide. But I think this data at least shows that you can definitely learn more information from having more sites, and specifically see what's happening in areas where people are consuming the most water. So now I'm going to shift gears a little bit and talk about implications on minimum residuals. And so my colleague David Wamman and I published a manuscript in the Journal of the American Water Works Association in August of 2015 called Distribution System Residuals: Is Detectable Still Acceptable for Chloramines? It was primarily focused on chloramines, but we recognized that residual maintenance is a barrier to contamination. There are many nuances of chloramines, and we've probably learned enough since the 1980s to desire continuous residual maintenance because we know much more about how distribution systems act as reactors. And so if that all is a goal, then we have to take into account the different disinfectant properties and recognize limitations in monitoring, such as those associated with organic chloramines. And so we felt that detectable is not acceptable for chloramines. Since that point, we're continuing our work in area of minimum residuals. We're doing some research on evaluating organic chloramine formation, including the impacts of nitrification and the resulting positive interferences on measuring disinfectant residuals. And we've worked with some of our colleagues in Office of Water on some evaluation of 6-year Review 3 disinfectant versus microbial data. And that's what I want to talk about now. Before I get into that data, here are two maps that are shown in our manuscript that show states that have requirements for minimum residuals that are greater than the federal minimum, which is detectable. And so there's about 20 states that have various different free chlorine minimum residuals that are higher than that. And then roughly the same states have requirements for total chlorine residuals that the range is a little bit wider in concentration, but it's mainly the same states. Okay, now jumping into 6-year review 3, for those that aren't familiar with the process, the 1996 Safe Drinking Water Act requires that EPA review each national primary drinking water regulation at least once every 6 years. So that means 6-year review 1 was 1996 to 2002, and it was published in 2003. So when they publish 6-year review, that they have candidates, regulatory candidates for review. So it means more information is now available that we should review this regulation and see if it should be redone. And so that was published in 2003, and the candidate for revision was the total coliform rule. And so that rule was then revised, and the final rule was published in 2013. So just to give a sense of how long it takes to publish a rule from 2003 to 2013. The second 6-year review was 2003 to 2009. The results of that were published in 2010, and you can see the revision candidates there. And then finally, 6-year review 3 was 2010 to 2015. There was a contaminant occurrence data set, an information collection rule for 6-year review 3, that from data from 2006 to 2011, and the results of 6-year review 3 were just published a few weeks ago at the end of December. And the revision candidates, and this information is all available on EPA's website. The revision candidates are chlorite, cryptosporidium, Giardia lamblia, haloacetic acids, heterotrophic plate count organisms, Legionella, total trihalomethanes, and viruses. And so I've colored in red those that are microbials and might be affected by chlorination. And now I'm going to go into that data from that data set. So states and entities, and these are all available on the EPA website, taken directly from the report that's referenced on the bottom of the slide. And so states and entities that are represented in the microbial data set, there are originally 46 states and entities. Entities are tribes, for example, shown here. There were originally 46, and then upon the QA, quality assurance, quality control review, several data sets from states had to be removed from that database. So the final result was about 33 or 34 states and entities represented in the data set. So the data set has paired data where each data point or each data entry is both a disinfectant entry and a total coliform or E. coli fecal coliform data point. So they're paired. And of all of that data, it's sort of represented like this Venn diagram here. So there's data that shows, let me back up a step. The utilities do not, there's no data that says if a utility is a free chlorine utility or a chloramine utility. So we have to do the best we can from the disinfectant data. So utilities that only reported free chlorine data, we assume they were free chlorine utilities, and there were 2.6 million of those records. Utilities that only report total chlorine data, there were 1.4 million of those records, and we generally assume that they were chloramine utilities. Some utilities report both free and total residual data in their samples, and there were about 770,000 records in that way, and those records are a little more difficult to determine. First, looking at the cumulative percent chlorine residual in surface water, this data is taken just from the year 2011. And what I really want to draw your attention to, well, let me just say first that the chlorine residual is on the x-axis here on the bottom. The cumulative percentage of samples is on the y-axis. And so if, for example, you look at a chlorine concentration of 1, go up to the free chlorine line, it happens to be at 50%. So that means 50% of the samples are below 1, and 50% of the samples in the database are above 1. And what I want to draw your attention to is down here at the bottom. And since we can't zoom in on this data, let's go look at the table and see that the percent of samples less than 0.2 for free chlorine are 8%, and for total chlorine are 0.9%. And the percent of samples less than 0.5, 18% of free chlorine samples, and 5% of total chlorine samples. So now we get into the data, looking at total coliform positives in surface water for the entire data range of 2006 to 2011. On the y-axis, we have percent of total coliform positives. The data is binned into ranges: 0 milligrams per liter, between 0 and 0.2, between 0.2 and 0.5, etc. And so let's start over on the right. The total chlorine residual over here, these are utilities that report total chlorine data. And as you can see, as the chlorine increases from 0 to 0.2 and greater than that, the percent of positives decreases, but there's not much additional benefit out here. Then when we look at the free chlorine residual, all of the free chlorine data, it's biased a little bit because of the many utilities that were probably chloramine utilities but happen to report both total and free chlorine. So if we remove that, the 770,000 samples I was talking about, you end up with the free chlorine data here on the left. And that shows a very similar result. As the chlorine concentration increases, the number of TC positives goes down. For E. coli and fecal coliform in the same data set, you see very similar results. And so as the chlorine residual increases, the number of positives goes down. Real quickly, as I'm getting to the end of the time here, if we look at groundwater and we look at total chlorine and free chlorine, this is basically the same analysis, but just with the two categories, because most groundwater systems are free chlorine systems, the data wasn't biased as much in the same way. You see basically a similar effect for both total coliform and E. coli and fecal coliform positives. So as the chlorine residual goes up, the number of positive samples goes down. And so just to summarize here, I went over federal regulations on the number of chlorine monitoring locations, which primarily leaves the determination up to the states through the sample siting plan. State requirements for sample siting plans are extremely diverse. We looked at a case study that shows some of the challenges in implementing monitoring location. And finally, data analysis for 6-year review 3 supports the relationship between disinfectant residual and microbial stability reported in the scientific literature. Thank you.
Okay, thank you very much, Jonathan. And so this ends our webinar for the presentations, and we'll follow it up with questions. Typically, we stay on for another 30 minutes, and I hope you can stay on with us, but we understand if you can't. Just a little note, if you have to leave, that our next webinar is on February 28th, and the title or the topic is source water protection. So that's February 28th for our next Small Systems webinar. So we'll go through a series of questions. A number of people have sent in questions. We'll try to get to them all in the next half hour. The first one is for Matt. What is the best method for testing chlorine residual in water systems with ammonia in the raw water? What is the best practice? What are the best practices to get consistent results?
That's a good question, and it really depends on where you are in the breakpoint curve, and that gets to how much chlorine you've added, and it gets back to also what concentration of ammonia you have in your raw water. So if you've achieved breakpoint, you should have predominantly just a free chlorine residual. If you haven't achieved breakpoint and you just form monochloramine, you could use the monochloramine residual method or also the total chlorine residual method. Where you run into problems is when you're in the second zone of the breakpoint curve, and that's where you have the combination of dichloramine, trichloramine there. And we have found through experience you'll get some kind of inconsistent results when you're in that zone of the breakpoint curve. So I think it's important to try to figure out where you are on the breakpoint curve. And a good way to do that, if possible, is to measure free ammonia residual. And if you do have detectable free ammonia residual, that should tell you that you should be having predominantly monochloramine. If you have no free ammonia residual, I would recommend measuring total chlorine and free chlorine. If you've achieved breakpoint, they should be relatively close or relatively similar. So.
Okay, thanks, Matt. Here's another one for you. What is an EPA-approved method, means of monochloramine disinfection residual testing, which can be done with a portable handheld device?
At this point, there's not an EPA-approved method specifically for monochloramine residual. Systems rely, I've seen just mostly the total chlorine DPD method for total chlorine, and total chlorine will be the sum of free chlorine, monochloramine, dichloramine, trichloramine, and also any other interfering compounds. But at this point, just total chlorine, the DPD method, is probably the most commonly used field method for chlorinated systems.
Okay, and thanks. And another one for you. Earlier in your talk, you mentioned high alkalinity and pH. What do you consider high alkalinity and pH?
Well, according to the manufacturer, an alkalinity above 250 milligrams per liter can result in not having full color development, or it can cause an artificially low chlorine residual result. High pH, I would say once you're up to around 10 or 11, that's when you might have some concerns. But what I would recommend doing after you analyze the sample, if you can analyze the pH of the sample with the DPD reagent in it, and it should still be within the 6 to 7 range if it was adequately buffered. If you've exceeded that buffering capacity, you'll have a higher pH.
Okay, great. Thanks, Matthew. Here's a question for Jonathan. Were the EPA hydrant flushing sampling kits used in the Flint, Michigan case study?
The hydrant flushers?
Yes.
Yeah, Matt and I both went up to Flint with Dave Foreman, and yeah, we used those flushers in Flint.
Okay, super. Here's another question for you. This person has seen quite a bit of data showing a total coliform or E. coli positive hit along with high chlorine residual in that sample, sometimes over 1 milligram per liter. How would you account for that?
I mean, that's not an easy one. With such high chlorine concentrations, generally you wouldn't expect that, except perhaps in sampling methodologies, contamination occurring during sampling and during handling, I suppose, is my best guess. Generally at such high concentrations, you don't see too much of that.
Okay, and one last one for you, Jonathan. How do you know if you have organic chloramines?
So organic chloramines are probably present in almost all waters at some very small amounts. Any water that contains natural organic matter, and all do to some extent, and then natural organic matter that contains very small amounts of nitrogen and ammonia, when you chloraminate, some of that will get tied up with these organic materials and be basically organic chloramines that show up in your chlorine tests, but don't in your total chlorine tests, but don't necessarily add disinfection power. And so that could be, a tenth or two in your total chlorine analysis, and oftentimes that's why a total chlorine analysis will be 1 or 2 tenths higher than the free chlorine analysis.
Okay, great. Here's one for Matt. Do you have a couple of questions on error in measurements? The first one is, do you have access to the study on sampler error leading to false positive results? And you mentioned a study on sampler error, I believe. And how would you go about assessing it if you were to do such a thing?
As far as a study on sampler error, we haven't conducted a study ourselves. A lot of the different items that I discussed have came from manufacturers' standard operating procedures, and also training that manufacturers have done, and also personal experience. Really, it's hard to say that this issue will give you this amount of error, or this issue will give you this amount of error. It's kind of just the culmination of various errors will compound and give you, or issues will compound and give you more error. So it's just kind of a best practice to try to you know, follow all the guidance or best management practices I discussed.
Okay, and the second question was, if you are using a DPD chlorine kit to measure the free chlorine residual in a chloramine system, will you get erroneous free chlorine readings, and if so, why? Does the ammonia interfere?
Well, this is maybe Jonathan or Dave could help with this question as well. I don't think it's the free ammonia that necessarily interferes with the free chlorine. I think it's just interference with monochloramine or other interfering agents.
You know, if you wait too long in a free chlorine test, the chloramines will start to bleed into that test. I mean, and quite honestly, if you have a chloramine system and you can measure that you have measurable free ammonia, you really don't have free chlorine, because free chlorine is going to react with the free ammonia. So yes, when you have a chloramine system, if you're measuring free chlorine, you can have some positive interferences.
Okay, great. And that was David Wahman, another researcher here at EPA, who is a co-author on this work. Okay, so here's a question for Matthew. How much interference are we talking about for DPD? Plus or minus 0.01, plus or minus 0.5?
I think this kind of gets back to the question I answered a minute ago. I think the more of these items that aren't followed, the more error you may have. So it's hard to say what amount of error scratch sample cells give you, or dirty sample cells, but you know, multiple issues can culminate into larger errors. So.
Okay, great. Here's one for Jonathan. For the state-specific sample site numbers, are the requirements for chlorine residual monitoring, the number of sites, typically the same for groundwater systems as surface water systems? Or perhaps Matt can touch on that one.
I'm not sure about that.
If the groundwater systems or surface water systems have the same number of sites, typically.
I believe that there's, I'm not gonna, I believe there's separate rules for groundwater and surface water. My expertise isn't as much as in the rules themselves. I know if it's a groundwater system that's under the influence, if it's a subpart H system, they would have the same number of sample locations as just a conventional surface water system would. So.
Okay, thank you. This one's for Jonathan. How does biofilm in the distribution system affect chlorine residuals?
So, you know, we know that biofilm is pretty much present in all systems. It's in the pipes to some extent in probably all pipes. And so how does it affect the residuals? You know, it interacts with residuals. It's really how does your residual affect the biofilm that's most important. So you want a residual in an attempt to interact and inactivate things that are in that biofilm. And that, I think, is why we desire continuous disinfection in our distribution systems. I think many, many years ago we felt that water treatment, you know, you would treat the water at the plant, and then when it left the plant, the entry point, you know, we just delivered it through these pipes, and it carried it to people's homes. And when it got to the homes, it was the same as when it left the plant. And you know, over 30 years or more, you know, we now understand that a lot more happens in the distribution system with water quality, and it's a big reactor, and there are a lot of different reactions going on, both with biofilm, organics, and inorganics at pipe surfaces, corrosion and things of that nature. And so we're, you know, there's not just us, but academia and practitioners all over are looking now at what's happening in distribution systems, and there are definitely biofilms, and they interact with the disinfectants.
Great, thank you, John. This is from Matthew. How do bubbles bias the sample results? Do they bias them high or low?
Both bubbles and condensation in sample cells will bias high, so you'd have artificially higher results.
Okay, great. How do you regulate the flow of your hydrant sampler? How accurate do you think it is?
We use a commercially produced flow regulating valve. The one we use for the hydrant sampler, it limits it to 20 gallons per minute. The manufacturer has they gave us some curves depending on pressure. It'll tell you what your corresponding flow rate is, but we haven't ourselves measured to determine how accurate that is. But we have pretty good confidence in it.
Okay, and you mentioned, and maybe I'll throw this out to both, but it was mentioned about overflushing. Can you expand on that comment?
Well, overflushing would be getting back to one of the flushing approaches I talked about. Well, flushing till you get a good result. So if you're at a location that actually has low chlorine residual, if you continue to flush, you know, you're not collecting a sample that's really representative of what's at that actual location. So. And that could be the same for disinfection byproducts as well.
Okay. Great. Okay, here's another question. This one is for, I think we've covered this a bit, but how is combined chlorine measured?
Well, combined chlorine would be the difference between free and total chlorine. Systems that chloraminate, they tend to use total chlorine to quantify disinfectant. Like I said, the monochloramine method is not EPA approved.
Okay, here's a question for Jonathan, and I'm not sure if you have these data, but in states with higher minimum chlorine residual requirements, do these states have more struggles meeting the DBP requirements than areas with less chlorine residual requirements?
Yeah, that's a good question, and I'm not specifically, I don't specifically have the data in hand to prove one way or another, and so it's not a simple and easy answer to show that. There's always a trade-off between, how much chlorine residual a utility carries and how much disinfection byproducts are formed. Drinking water treatment is balancing multiple risks. And, we're balancing, risks from microbial pathogens and risks of disinfection byproducts. And they're both very important. But we have to assess both of them. And I certainly think with what we know today about, the nature of microbial pathogens and Legionella, that we definitely need to provide continuous disinfection residual.
Okay, yeah, that's good. That answered a couple other questions. Also, here's one, and I think it kind of, and I'm kind of blending a couple questions together here, but in systems that have higher chlorine residuals yet come up E. coli or total coliform positive, can you talk about the ratio between hypochlorous acid and hypochlorite ion and how that might impact the results? Maybe throw that to Dave.
Well, I mean, if we think about free chlorine, we generally think about hypochlorous acid being the effective disinfectant, and based on pH, as you increase pH, you're favoring the hypochlorite ion. So pH 7.5-ish, you're about 50-50 hypochlorous acid and hypochlorite ion. I mean, I can't tie this to the higher detections at higher residual levels, but in general, as pH decreases, you're favoring the more effective disinfectant, which is hypochlorous acid, which you'll see in the CT tables, has lower CT values because of that. And then at higher pH, you're favoring hypochlorite ion. So in essence, you think you're maintaining probably a less potent disinfectant, but you're still maintaining a disinfectant.
Okay, thanks, Dave. Here's a question. I think I'll throw it to Matt, but perhaps others can answer it. If I sample at a site that has a free chlorine residual at 0.5, but my pH is 11+, should I be concerned? So this fits kind of a segue then into that question or answer.
Well, as I mentioned earlier, at higher pHs, it tends to suppress or give you a negative interference on your results. What I would suggest doing, like I said before, measure the pH of the final sample. When I say final sample, that's the sample with DPD reagent, and if it's in the 6 to 7 pH range, you should have confidence in that data. If it's higher, that would suggest there's an interference.
And so 11+, where does that throw you in terms of hypochlorite ion?
It's pretty much all hypochlorite ion at that pH. I mean, so you figure it, like I said, pH 7.5, you're about 50-50, and then as you move one pH unit, so 8.5, you're 90-10, 9.5, you're 99-1. only about 1% is hypochlorous acid when you're getting into that range or lower.
Okay. Here's a question. I think it was mentioned in both talks, and I don't think we covered it exactly, but how do you ensure proper flushing when sampling? So does someone want to start with that?
Talk about the procedure.
Yeah, so I kind of covered this, I guess, in my presentation. We developed the calculated flush time procedure, and basically that's just based off of estimating the volume of water that you need to displace between the sample location and the main, and then determine whatever the flow rate is while you're flushing. And if you know that, you could determine how long you need to flush at that flow rate to displace that amount of water. As I mentioned earlier, we like to use the factor of safety to ensure you're getting in the main. You don't want to overflush, like one of the questions I answered earlier, because that might, provide biased results. But you don't want to underflush either, because then you're not accurately characterizing the water in the main. You're characterizing water in the service line. So, so we recommend using that calculated flush time procedure.
Yeah.
Okay, good. Here's a question that's related to the one I asked you previously about the bubble bias. And you mentioned temperature also. So when you're at a system that has high or low temperature, or perhaps with bubbles, how would you try to control that bias then?
With the bubbles, we'd recommend just inverting the sample cell or tapping it to make the dissolved gas or those bubbles go away, and just visually confirming that it's not there. If there's condensation, also wipe the cell. But it's always good to check that before you read it in your instrument.
Temperature, it's mainly for the monochloramine and free chlorine indophenol methods, more so, right?
It tends to cling more to those plastic cells. They're not circular, and it catches in the corners, yeah, of the cell.
Okay, great. Here is a question for Jonathan. You put up the maps, but can you talk a little bit about the additional sampling sites in Flint? How were they selected, and how does it relate to distance from the water source, or perhaps pipe diameter, and how the interplay between those two?
Yeah, when we were in that project, we looked at what we really wanted to do was get in the neighborhoods and get closest where people in the city were actually using and consuming the most water. And so we looked at the smaller distribution lines, those in the streets and the neighborhoods, and that's where we wanted to get closest to. And so, we also looked, at all distances from the treatment plant, from closer to further away. And so we took all of those issues into account as we went and looked for these schools and churches and child cares that were, what I'll say, embedded in the neighborhoods and closest to those consuming the water.
Okay, great. Thank you, Jonathan. Let's see, I'm trying to find a question we haven't answered already, but let's see. How do, we answered that. Maybe we're coming to the end of our questions here. So, all right, here, it's a related question. Here's a question about the Hawk test kits, perhaps, that we could answer. What do you think about the high and low range Hawk test kits? Do you have a comment on that? You mentioned using ranges in your talk, Matt.
Yeah, one thing you want to be careful about, which I kind of got to in my talk, there's a particular model out. It measures both high range and low range. I would recommend if you're in the low range, which is less than 2 milligrams per liter, using that range, because you're going to get more precise results. So it will give you a reading out to 100th of a milligram per liter. The trouble when you use the high range method and you actually have a lower residual, you just don't get the precision, and it's likely less accurate. So.
Okay, great. Thanks, Matt. Here's the question that we didn't touch on. What is the value of lining concrete water storage tanks in an effort to maintain residuals? Do we have some experience with that?
I do not have any experience with that, no.
Okay.
Yeah, no, neither do I.
Okay, correct.
I think there's a lot of information out there on making sure tanks are properly mixed and not stratified to help improve water quality and residuals. But the lining part of it, I'm just not familiar with.
The only thing I could think of, if it's concrete, you could have some influence on pH, and that could affect water quality.
Okay, here's a kind of somewhat related question, but completely different. So this person is aware of 2 elevated redwood tanks made out of redwood.
Oh, okay.
That apparently the city's water is placed into those tanks, and they're elevated tanks to serve a hospital with additional pressure. So have you ever run into situations where water tanks are made out of wood, and perhaps you can expound on some of the problems that may ensue with that material?
I can't say I've never seen a tank made of wood.
Yeah, I've never seen a tank made of wood. Yeah. Issues with the material.
Yeah,
I mean, it could be porous, I guess.
I would assume it's lined in some way. Otherwise might water leak out.
Yeah.
Don't really know.
One might hope, right?
I would like to see those tanks.
So, okay, so I guess the answer is...
I think that's a site-specific kind of question that
yeah.
We'd have to know more information.
And perhaps the hospital might want to look at their system in terms of what water quality is coming out, would you say?
I would suggest that. Yeah.
So would I. I think that answers our questions. Thanks for all the questions. I tried to combine a bunch of them. I tried to get all of them, and we've gone here 25 minutes. So I think we've touched on them all to some degree. So thank you so much for your time and listening into our webinar series. I'd like to thank our speakers, Matthew Alexander and Jonathan Pressman, for their outstanding talks today. And thank you for listening. And to come back next month, again, February 28th, we're doing a source water protection webinar series. Again, 2 talks with questions. So we'd love to see you there. And with that, this concludes our webinar.